In this video, we're going to do more with systems of equations, but instead of just having two equations with two variables, we're going to have three equations with three variables. So we're going to learn a technique to use to solve systems of three linear equations like this. And then in the next video, we're going to learn another method that can be used to solve all of these different systems of linear equations using matrices. But we're not doing matrices yet in this particular video. This video is going to be a lot more similar to the last one, just has a little bit of extra steps, and it's going to be mostly examples. So first, let's learn the technique that we're going to need to solve a system of three equations with three variables. First, we need to write each equation in the standard form, which is the ax plus by plus cz equals d. So each equation needs to be rewritten in this way with all of the variables on one side and the constant on the other side. Step 2. Choose a pair of equations. And eliminate one variable using the elimination or addition method. So that's the method that we learned in the last video. So out of your three equations, you're going to choose any two that you want. And then you're going to eliminate one of the variables out of those two equations. Step 3, you're going to choose a different pair of your original three equations. And you're going to eliminate that same variable. Then you're going to solve the system made of the equations that we get from step 2 and step 3. So what we've done at this point is we've taken our three equations, chosen a pair two different ways, eliminated the same variable from those pairs, to create a system of two equations in two variables, which we already know how to solve from our last video. So then we solve that, and the last step is to substitute the info from step 4 into an original equation to solve for that last variable. And then you're done. So basically, the technique that we're using to solve a system of three equations with three variables is first play with it to create a new system of two equations and two variables. Solve that like we already know how to, and then use that info to find the last variable. It sounds way more confusing than it actually is, so let's just go ahead and do an example to make it a little bit more clear. (2x minus y plus 5z equals -7. X plus 4y minus 2z equals 1. 3x plus 2y plus z equals -7. So I have three equations here with three variables. And the first thing I have to do is pick two of the equations and eliminate a variable from them. So I'm going to choose to use equations 1 and 2. So 2x minus y plus 5z equals -7. X plus 4y minus 2z equals 1. And I'm going to choose to eliminate the y. And the only reason I'm eliminating the y is because they already have opposite signs there. So to eliminate the y, I can multiply the top equation by 4. And when I do that, that top equation becomes 8x minus 4y plus 20z equals negative 28. And my bottom equation is still the same as it was before. Now when I add those two equations together, the y will be gone. Add the two equations together and I get 9x plus 18z equals negative 27. And that's an equation with just two variables in it. So I'm going to keep track of this because we're going to need it. And now I go back to my original three equations and choose a different pair. And I'm going to choose equations 1 and 3. So if I choose equations 1 and 3, equation 1 was 2x minus y plus 5z equals negative 7. And equation 3 was 3x plus 2y plus z equals negative 7. And I'm going to eliminate the same variable, so I need to get rid of the y. To get rid of the y, I can multiply my top equation by 2. So the top equation is now 4x minus 2y plus 10z equals negative 14, and my bottom equation has not changed. When I add these two equations together, I get 7x plus 11z equals negative 21. So now I have this equation up here and the equation down at the bottom are two equations with two variables. We can solve that using our techniques from the last video. Let me write that second equation up here by the first. All right, so now this I can solve using either substitution or elimination. And the first thing I honestly would do is I look at this first equation up on top, and I notice that all of the numbers are multiples of 3. So I'm even better, they're multiples of 9, actually. So I can make my numbers simpler by dividing everything in that first equation by 9. Then I have smaller numbers to deal with. If I divide everything in the first equation by 9, we get x plus 2z equals negative 3. And then my second equation did not change. So if I'm going to try to solve this with either substitution or elimination, I would probably do elimination. And what I would do is eliminate the x. Then I can just multiply the top equation by negative 7 to eliminate the x. When I multiply by that negative 7, get negative 7x minus 14z equals 21. And I have 7x plus 11z equals negative 21. Add the two equations together, and the x's go away, and I get negative 3z equals 0, which means that z is 0. So now I've gotten one of my variables. I just need to find x, and then once I have x, I can plug x and z into an original equation to get y. So this z equals 0, I get to plug it into one of my two equations. And I would plug it into this x plus 2z equals negative 3. So since x plus 2z is equal to negative 3, That means x plus 2 times 0 is negative 3. X is negative 3. So now all I have to do to finish solving the system is take these two answers and plug that into one of my original equations. And it doesn't matter which equation we use. So I'm just going to use the first equation. My very first equation was 2x minus y plus 5z equals negative 7. So I'm going to plug in all of my info. And I get negative 6 minus y equals negative 7, which is the same thing as y equals 1. So the solution to this system is the ordered triple. X is negative 3, y is 1, and z is 0. So just like when we had just the system of two equations, we had points as our answers. This is like a point too. It's just a point in 3 dimensions instead of just 2 dimensions. And instead of thinking of lines intersecting, think of planes intersecting. So just imagine floating sheets of paper and how they can intersect with each other. All right, let's do another example. I have A plus 3C equals 4. B plus 2C equals negative 1. And 2A minus 4B equals 14. So this is another system of 3 equations, and I do have 3 variables, even though I don't have all 3 variables in every single equation. That just means for a particular equation, we have a coefficient of 0 for a certain variable. I still need to try to eliminate a variable by choosing 2 of the equations. If I choose equations 2 and 3, B plus 2C equals negative 1, 2A minus 4B equals 14. If I multiply the top equation by 4, then I can eliminate the B's. So I have 4B plus 8C equals negative 4, 2A minus 4B equals 14, and when I add those 2 equations together, I'm going to have a 2A and an 8C equals 10. So take a look at this equation we got by doing that. It has A and C in it. And if I look back at my original equations, that top equation already has A and C in it. So I'm going to match those 2 equations up and solve that system of equations. So I have A plus 3C equals 4. And then I have this new equation that I got of 2A plus 8C equals 10. Now I can solve this system for A and C. And the first thing I would do is go ahead and divide that second equation by 2 just to make our numbers smaller. A plus 3C equals 4, and A plus 4C equals 5. And now let's solve it by elimination. I am going to go ahead and multiply the top equation by negative 1. That would make this negative A, a negative 3C, and a negative 4. Now when I add those equations together, the A's go away, and I have C equals 1. To find A, I just take this C equals 1 and plug it back into one of these equations. Let's just use the bottom equation. A plus 4 times 1 equals 5. So this means A equals 1. So both A and C are 1. And to find B, I can just plug this info into one of my original equations. Well, one of my original equations is B plus 2C equals negative 1. If I plug in C equals 1, I get B is equal to negative 3. So my ordered triple for this one is A is 1, B is negative 3, C is 1. And that is the solution to the system of equations. So even when all of the equations don't all share the same variables, you can still use this technique to solve it. You just have to play with them enough to get two equations with two variables and then back substitute appropriately. Let's do another couple of examples. X plus y plus 4z equals negative 1. 3x plus y minus 4z equals 3. And negative 4x minus y plus 8z equals negative 2. Well, I'm going to go ahead and I'll be eliminating y's because I can pair up equation 1 and 3, just add them together, and then pair up equation 2 and 3 and add them together. And it's already set for elimination. So equations 1 and 3, I have x plus y plus 4z equals negative 1. And negative 4x minus y plus 8z equals negative 2. If I add those two equations together, I get negative 3x plus 12z equals negative 3. Which notice already that all of these are multiples of 3, and in fact multiples of negative 3. So I'm just going to go ahead and divide all of those by negative 3 to get x minus 4z equals 1. All right, so that's what I get from looking at equations 1 and 3. Now I'm going to look at equations 2 and 3. And let me go ahead and write down what we found already. X minus 4z equals 1. All right. So looking at equations 2 and 3, I have 3x plus y minus 4z equals 3, and negative 4x minus y plus 8z equals negative 2. Adding the two equations together will eliminate my y. And I'll get negative x plus 4z equals 1. Now I can take this equation and pair it up with this equation that we got before. I have x minus 4z equals 1 and negative x plus 4z equals 1. And it's already set up for elimination. My x's are opposites. Add the two equations together, and I get 0 equals 2. So what does that mean? It just means it's no solution. Just like when we had just equations with two variables. It's possible to have no solution. So if you're doing this sort of system of equations like this, and you get something that's complete nonsense, like 0 equals 2, you know it's no solution. Let's try another one. 5y plus z equals 0. Negative x plus 4z equals 0. And negative x plus 5y plus 5z equals 0. And so I'm just going to take the bottom two equations and I'll eliminate the x. So if I look at equations 2 and 3, I have negative x plus 4z equals 0, and negative x plus 5y plus 5z equals 0. And to eliminate the x, I just have to multiply my top equation by negative 1. And that just changes my signs. Negative 0 is still 0. And when I add these two equations together, the x's are gone. And I get 5y plus z equals 0. And now let's compare that to our other equation that has just y's and z's. The other equation is 5y plus z equals 0. Well, that's interesting. They're the exact same equation. And what that means is if I try to solve this system by elimination, so let's just multiply the bottom equation by negative 1, add them together, you're going to get 0 equals 0, which is a true statement. So that means there's infinitely many solutions to this one. And we just have to figure out how in the world to write our answer. So this is infinitely many solutions. And there are a lot of ways how to write this in terms of one variable or another. I personally think the easiest way is let's take these top two equations and solve them for both x and for y. So if I take my top equation and solve it for y, I get y equals negative z over 5. And if I take my other equation, negative x plus 4z equals 0, and solve that for x, I have x equals 4z. So now that I have two of my variables written in terms of the third variable, I can write my solution set as the set of all points where the x is 4z, the y is negative z over 5, and z is z, such that z is a real number. And that's just one way to write the solution to this particular system. We could have solved for y and z in terms of x, or for x and z in terms of y, and written it in many different ways. I just chose the way that seemed the simplest to me. All right, let's do one more example of a system of 3 equations and 3 variables. And then that will be it for this video because we're going to learn other techniques for solving these in the next one. So our last example. Given the non-collinear points, negative 3, 2, negative 4, 1, negative 6, negative 7, find an equation of the form y equals ax squared plus bx plus c that defines the parabola through the 3 points. So right now, you're probably looking at this problem and thinking, that doesn't look like a system of equations. What's going on? But you know what? It is a system of equations. We just have to find the equations first. We're going to set up a system to solve for A, B, and C. To do that, we're going to take each of these points and plug it into this y equals ax squared plus bx plus c. So plug the points in, and that will get us our system of equations. When I plug in the point -3, 2, I get 2 equals a times -3 squared plus b times -3 plus c. And that simplifies to 2 equals 9a minus 3b plus c. That is one of my equations. Now let's plug in our next point, -4, 1. That gets me 1 equals a times -4 squared plus b times -4 plus c, which simplifies to 1 equals 16a minus 4b plus c. And there's equation 2. When I plug in the third point, I get my third equation. My third point was -6, -7. So I get -7 equals a times -6 squared plus b times -6 plus c, which is -7 equals 36a minus 6b plus c. And that is my third equation. So when I take the 3 equations that I have boxed up and solve that system, I'll solve for my coefficients a, b, and c. Then I can just plug those in and I have the equation for the parabola. So let me rewrite just with our 3 equations so we can solve this system. We have 9a minus 3b plus c equals 2. 16a minus 4b plus c equals 1. And 36a minus 6b plus c equals -7. And I think the easiest variable to eliminate is c, because I can pick any 2 pairs of these and then just multiply one of the equations by -1 and add them together. So let me choose equations 1 and 2 to start with. And I'm going to multiply my top equation by -1. That changes all my signs. Now when I add these equations together, I'm going to get 7a minus b equals -1. And that is going to be one of my equations with 2 variables. Now let's do the same thing, but I'm going to use equations 2 and 3 this time. So using equations 2 and 3, equation 2 was 16a minus 4b plus c equals 1, and equation 3 was 36a minus 6b plus c equals -7. And again, I'm going to multiply the top equation by -1 and add the equations together. That will give me 20a and a minus 2b equals -8. And now I have a system of 2 equations in 2 variables. So my first equation was 7a minus b equals -1. My second equation is this 20a minus 2b equals -8. But I'm going to go ahead and divide all of that by 2, just to make my numbers smaller and easier to deal with. Now to solve this system of equations, I'm going to again multiply the top equation by -1. That changes all my signs. And when I add these equations together, the b goes away. And I get 3a equals -3, which means a is -1. So I have one of my coefficients for the parabola now. A is -1. To find b, we just use one of these equations that we just found. I'll use the 7a plus b, or 7a minus b equals -1 equation. My a is equal to -1, so when I plug that in, I get -7 minus b equals -1, which is the same thing as b equals -6. And now, to find c, all I have to do is just take one of my original equations. I'll use the first one because the numbers were the smallest. 9a minus 3b plus c equals 2. And just plug our stuff in to figure out what c is. 9 times -1 minus 3 times -6 plus c equals 2. That's -9 plus 18 plus c equals 2. So this is 9 plus c equals 2, which means c equals -7. So now I have a, b, and c. But the question was asking me for the equation of the parabola that goes through those 3 points. And it said my parabola should look like ax squared plus bx plus c. But now we know a, b, and c. So the parabola that goes through all those points was -x squared minus 6x minus 7. And that parabola right there is the final answer, and it goes through all 3 points that we were given. So that was just an example to show you something you can do with a system of 3 equations that you might not have thought about before. In our next video, we're going to continue solving systems of equations, but we're going to learn how to do it using a matrix to organize our information. It's equivalent to all the stuff we've already been doing, but I personally think that with larger systems of equations, the matrices are easier. If you have any questions, feel free to drop them below, or come to office hours or email if you're one of my current students, and I will see you for our next video on solving systems with matrices.